Kirchhoff's laws. There are two of them. This one wants the second. Remember, the first is going to be current, alphabetical, and the second is going to be voltage. So the voltage, it really means that when you complete a loop, any loop, and if it's in series like this, it's only got one loop, that the voltage, the entire voltage, or the EMF of any loop must be closed. And what I mean by closed is it means to be all used up. So the entire EMF of the battery is going to be completely used up when it is closed for Kirchhoff's second law. We got a battery, electromotive force, 9 volts. So that's the entire ability of the battery, which is kind of silly because technically this is a double battery, so 2 batteries make 9 volts. Negligible internal resistance is connected. We got one of them that is a variable resistor, that's resistor X, and then we have another thermistor, which is resistor Y, so you got the symbols there. And then they have a graph that shows you that the thermistor is going to change its resistance with temperature. All of this graph means nothing for part I, which says that the current going through this is 1.1 times 10 to the negative 2, so not a lot of current, and the potential difference across resistor Y is 4 volts, and we want to determine the resistance of X. 2-point question, so that normally means formula, plug it in, you're done. So 4 volts is resistor Y. So if we have 4 volts here, that means that resistor X is going to have to use 5 volts because, again, according to Kirchhoff's second law, any loop must use up all of the voltage, all the EMF. So 4 plus 5 makes 9. And now we know that the voltage across Y is going to be 4 volts. What is the current that's going to go across Y? According to the problem, the current is going to be 1.1 times 10 to the negative 2 amps. So 1.1, 10 to the negative 2 amps. And then we use Ohm's law. I is equal to V over R. 1.1 times 10 to the negative 2 would equal 4 divided by R. And you just solve, which ends up flip-flopping those. R would equal 4 divided by 1.1 times 10 to the negative 2. Calculator. 4 divided by 1.1 times 10 to the negative 2 power is 363. I'm recording.
Oh, shit. Is it supposed to be 5 and not 4?
Yes, it's supposed to be 5 and not 4. You are redeemed of all qualities. Reagan, I don't want to hear that I don't mess up. Like you claimed it. 454.54. I could have just looked at my answer key the whole time. 2 amount of sig figs. I feel like we're going to only have 2 sig figs. I wonder what the answer key did. The answer key also only did 2 sig figs. Paper 2, even though they mimic sig fig rules almost the same way as the lab does, they don't always grade on it. Okay, so like the answer key says 450, but there's nothing that says you can't write 454, which means you can still get credit for it. Very rarely will they care. All right, temperature in resistor Y is changed to 190 degrees Celsius. So that's hot. 100 degrees Celsius is boiling. That's like double boiling temperature almost. Resistance of X is unchanged, so that's going to stay at 450. Determine the new potential difference across Y. So we need to now use this chart. They said the temperature was 190, so we're going to use this chart to figure out if we have 190 degrees, which is like there. That looks like it is going to be 25 ohms of resistance in resistor Y or X. I don't remember which one's which. Resistor X is now going to be 25 ohms. So if this is 25 ohms, resistor Y is how many ohms? X is how many ohms? Good grief. I've mixed them up again. Resistor X is 25, is 450, and oh my, X is 450, Y is 25. It'd help if this was on like one little piece. 450 for one, 25 for the other. 450 never changed. 25 is now what resistor Y is going to be. What is the actual question? Find the voltage on Y. You have 2 resistors in series. You can choose to either use Kirchhoff loop rule, or you can just say I is equal to V over R. What is the voltage that they're going to have to use? 9 total. What is the current? Well, that's what we're looking for. And we have the total resistance is 450 plus 25 would make 475. Finding the new current. Very, very small current. 9 divided by 475. 475. The current is 0.0189. I do not recommend rounding that early. How do we find the voltage across resistance Y, which is the potential difference? You just take that current and multiply by the resistance, which is 25, and you get a voltage of 0.47 volts. 0.47 volts. All right. Last question's kind of like wonkadoodle off to the side because I was saving paper. The resistance of X has increased. The temperature of Y remains at 190. If resistance X increases, that means that the resistance total also increased, which means several things have happened. By reference to the current in the circuit, state and explain the effect of this change, if any, on the potential difference across Y. The potential difference in series will be given to the resistors with the most resistance. If resistance of X goes up and resistance of Y stays the same, that means that more potential difference will go to X. Potential difference of X would go down, which means the potential difference of Y. Potential difference of X would go up, which means potential difference of Y would have to go down because it has to total to 9 volts again. Actual answer, key answer, says something very similar. It says resistance of X increases, so total resistance increases. Current, therefore, decreases. Potential difference across the thermistor would decrease. A lot of chain reaction things happening there. Be careful with your ups and downs. That makes it tough. 7 minutes 30 for the first one. We're on good time. Are you taking photos of it? I'm going to publish the video. It's going to be available. Speaking of videos, I added an extra credit video this morning. Been doing a lot of recording. All right. Thermistors and LDRs. I think I've done this one in the past. A battery is connected to a circuit with a light-dependent resistor. That's the one with the lights, like the arrows. 2 fixed resistors, voltmeter reading here. The battery has an electromotive force of 25 volts. Negligible internal resistance. 2 resistors are 320 and 240, all of which that is just in the diagram. So, the voltmeter displays 16 volts. So that means that across this resistor we have 16 volts. Which means that the voltage of both of these is going to be 9 volts. Thanks to Natalie for telling me that on Tuesday and me remembering it, or Monday. I don't remember. Wednesday. Way off on the days. 9 volts because 9 and 16 make 25. And because these are in parallel, they get the same voltage. We can use that 9 volts to figure out the current going through the bottom resistor. So you can use I is equal to V over R, Ohm's law. 9 divided by 240 would equal the current going through that. 9 divided by 240 is 0.0375. 0.0375 is the current going through that bottom section. I think we're getting a little ahead of ourselves because in the beginning it just wants us to show that the current is 0.05 amps. But we're going to use that 0.0375 at one point. So how do we show that the current is 0.05 amps? Well, we could just do the same sort of idea with the 320 and the 16. Because I is equal to voltage divided by resistance. It's almost the same formula every time because that's the only formula you got. I would equal 16 for that one resistor divided by 320, and that does equal, hopefully, 0.05, and it does. So that is the proof that we needed for that one. All right. Knowing that that current going in through here is 0.05. Knowing the current going through the 16 volt and 320 ohm resistor is 0.05, knowing that that junction here split the current up. And we have, according to our first part, 0.0375 this away. We could figure out how much we have current-wise going on the top because the current got split. So you would take the 0.05 minus the 0.0375 and get 0.0125 for the top current, which is needed to be able to calculate the resistance of the LDR. Now that we know the voltage and the resistance of the LDR, I is equal to V over R, 0.0125 is the current going through the LDR, that one up top. The voltage is 9. The resistance can be calculated by just dividing. 9 divided by 0.0125 gives us a resistance of 720 ohms. All right. Power dissipated by the LDR and power dissipated by the 240 ohm resistor. You have options for that. We know the current, we know the voltage, we know the resistance. I would just say I times V over I times V for both, and you just divide. The current going through the LDR was 0.0125. We found that out before, 0.0125. The voltage going through that was 9. The 240 ohm resistor was the bottom one, which had a slightly smaller current, and that had a current, a bigger current, 0.0375, and it also had 9 volts. The 9s cancel, but if you don't cancel them, it's still fine. You end up with 9 over 9 that cancels, and 0.0125 over the 0.0375 is 1/3, if my math is correct, and it is. Answer key says 0.33, which is also 1/3, but I don't like that they didn't repeat it, which bothers me, but that's not my thing to say. Okay. The intensity of the LDR increases. If intensity increases, the resistance of that resistor goes down. Okay? So the resistance of that resistor would go down. So if this resistance goes down, what is going to happen to everything? Well, several things will occur. The resistance here would go down, which makes the resistance of the parallel section also go down. All right, so when you have resistors in parallel, if their resistance goes up, the overall parallel part goes up. Thanks to Dylan for helping me out with that one. And if you add more resistors, the resistance would also go down. But if you change this resistance to going up, the overall resistance of the parallel section would go up logically. All right, but adding more resistors always decreases the resistance in parallel. Adding more resistors always decreases. Adding resistance adds resistance. Decreasing resistance decreases resistance as normal. If this resistance goes down, that means that the current on this side would go up, but I don't think we need to know that. For our question, it says, what will happen to the voltmeter? The voltmeter's over here. If we make this overall section, if that resistance equivalent goes down because we made the LDR brighter and therefore made that resistance less, if this resistance goes down, that means that this resistor, the 320, its proportion goes up. And if that resistance proportionally goes up, not the actual resistance, but proportionally goes up, that means it's going to draw more of the 25-volt battery. Okay? So the resistance total goes down. Therefore, this is the therefore symbol, the current will go up, and the voltmeter will increase. I like thinking of it in terms of this resistance went down, therefore the other resistance would have to proportionally go up and therefore draw more voltage of the battery. That's how I like to view it, but typically answer keys like saying voltage resistance total goes down, therefore the current goes up and the voltmeter will increase because the volts are divided by resistance and you get the current that way. I don't know. Meh. 2 down. That one was even quicker. This one might slow down. We'll see. Drift speed and internal resistance. Sheet 3. Battery electromotive force is 8 volts. We have an internal resistor this time. We have a parallel section. We got an easy question in the beginning. It just wants to know what is the current going in the battery. And if you look carefully, we got 0.45 here, you got 0.49 there. Those had to come from somewhere, and if you add them up together, you get 0.94 when you add up these two. For some reason, I thought it was 0.95. So that means the current going through the battery is also 0.94 because what goes in had to leave, 0.94. And that would also be what is flowing through the battery is 0.94 amps. Okay? One pointer, not hard. Determine the internal resistance of the battery. So we have to do a little bit of thinking here. And you have to think, what do we have two pieces of information on? If you have two pieces of information, you can actually find the answer. What a lot of people made the mistake of was thinking, oh, the voltage that this little r is going to use is 8. 8 has to be used up by everything. It's not going to get used up exclusively by the little internal resistor. What we should figure out first is, see how we have amps and resistance? We can figure out the voltage on the bottom strand or the voltage across Y. I is equal to V over R. I times R would equal V. 0.45 times 16 would equal the voltage across Y, which happens to equal 7.2 volts. So if this voltage is 7.2, that means that the voltage across X and Y, X and Z combined would also equal 7.2. But that really means that we have 7.2 used up on the outside of the battery, which if we have 7.2 used up on the outside, if you do 8 minus 7.2, you get 0.8 volts used up on the inside of the battery, which means that here you get 0.8 volts going across that little internal resistor. And if you got 0.8 volts going across there, and you have the current going through it as 0.94 amps, now you can find the resistance of that battery, which I would say is I is equal to V over R. 0.94 is equal to 0.8, the voltage that the little guy used up, divided by R. And if you divide 0.8 by that, 0.8 divided by 0.94, you get a resistance of 0.85 ohms. Not a lot of internal resistance, and that is actually normal for there not to be a lot of internal resistance. Okay? All right. Resistors X and Y in figure are made of wires of the same material, same cross-sectional area, and average drift speed of 2.1 times 10 to the negative fourth meters per second. The average drift speed of the free electrons of Y is what we're asked to find. So here we have to use I is equal to A, N, V, Q. There are a few different tricks you could use here, but I'm just going to go through it as if you didn't know any tricks. We know the current going through X, and we know the drift speed going through X, so I am going to use that first. The current going through X is 0.49 because it had to go through both X and Z was 0.49. So 0.49. You do not know your A. You do not know your N. You are provided your V, 2.1 times 10 to the negative fourth. You are also, hopefully, knowing your Q is the charge of an electron, 1.6 times 10 negative 19th. You can solve for A and N simultaneously. 0.49 divided by a whole bunch of stuff. 2.1 times 10 to the negative fourth. 0.49 divided by 2.1 times 10 to the negative fourth, and divide by 1.6 times 10 to the negative 19th. Be sure to use parentheses when you're doing this, otherwise it will not work out. It'll divide by 1.6 and then multiply, and then it won't give you the right answer. You get A and N. That doesn't seem right. Uh-oh. Oh, maybe it is. It's the number of electrons. It's quite a few electrons. So I got AN is equal to 1.4853. Hopefully I did my math right. You're going to use that AN to do what is the drift speed going through Y? Because the AN is the area of the wire and the number of electrons in the wire. If it's the same wire, then it's going to have the same amount of electrons per unit volume and the same area. So we're going to just change out the current to figure out the drift speed going through Y. So it's going to be 0.45 is equal to AN, which we just found out, 1.4853. We're looking for V, 1.6 times 10 negative 19th would be our Q. And you just solve for V there. 0.45, divide by that, and divide by 1.6 times 10 to the negative 19th power. And you get a velocity that is very slow. Drift speed is very slow. It is 0.00019. Okay? Oh. I didn't in my calculator. I just used answer. So at least my answer's right. All right. There are a lot of math tricks that you could use to make that problem a lot quicker. I don't necessarily recommend them because they're singletons. Like, you only get to use that trick once. But knowing that, like, AN is the same and Q is the same, a lot of things would end up canceling if you decided to set up the equation simultaneously, and that would have made it a lot easier on your calculator. All right. I liked Part D. Part D is, like, a normal type of question at the end of almost every AICE exam for, like, current. They decide to do something new. Resistor Z in the circuit is now replaced with one with a smaller resistance. State and explain the effect, if any, on the terminal potential difference. So that would be the voltage on the outside as the terminal difference of the battery. So we replaced it with a new smaller resistance. If you replace anything with a smaller resistance, the resistance is going to go down. Unless you added a new resistor in parallel, that'll be the only time that, like, it won't mimic what you would think. So if you add a resistor in parallel, add a resistor, resistance goes down. But if you just change it to something that's smaller, resistance goes down as well. Anytime you have resistance go down, what happens to the current? Current go up. Okay? But think proportionally. If we have less equivalent resistance on the outside, how does that mean that the little internal resistance on the battery is going to behave? It's going to be like, well, now I'm a bigger guy, and I'm going to steal more voltage because I feel more powerful. So the resistance on the inside, proportionally at least, is larger. But the resistance total on the outside is smaller, and therefore the potential difference at the terminals will decrease. I'm not good at writing with words. I wrote out. And we got one left. And I'm going fast because I figured nobody's going to want to watch a video if I go too slow. The last one, I think we'll go quick, but it is by far the weirdest one. All right. We're going with the AICE definition of electrical potential difference, by the way. I like saying electrical potential difference is voltage, just plain old voltage, but that's not a definition. The one we did yesterday was the energy transferred from electrical forms divided by charge to other electrical forms. I forgot to write to other electrical forms. I'm just kind of hoping they don't ask for us to define that, because every other idea of what I think of as potential difference, that doesn't help. All the other ones where we define something, it normally helps, like Ohm's law, I is equal to V over R. You need that anyways. Okay? We got, oh, this is a weird one. A wire with a cross-sectional area of A is made of a material with resistivity of rho. The wire is extended. Assume the volume of the wire remains constant as it extends. Show that resistance R of the extending wire is inversely proportional to A squared. This one I was not prepared for, but we're going to try it anyways. R is equal to rho, length divided by area. Okay. We extended the wire but we had to keep the volume the same. So if you extend the wire, that means that the area is going to get smaller. Do we agree with that? Like it'll stretch the wire out and the area will get smaller. Volume is equal to length times area, just because it's like the formula for volume. Length times area is equal to volume. So we could say that the volume is staying the same, and therefore Struggletown. We could take area and replace it. Well, we don't want to replace area. We want to replace length. Length needs to be replaced with volume divided by area. Agree with that? Okay. So resistance would equal rho, volume over area, divided by area. But then the areas end up... Oh, nope. No, they don't. Resistance would equal rho, volume, over area squared when you do the math. The volume's held constant, the rho's held constant, and there we got our proportional, inversely proportional to area squared. That was a weird one, to say the least. That's not the reason I picked this problem. I picked this problem because the internal resistance graph that we have next. We got a battery hooked up to a single resistor, and it has a single internal resistor as well. We got a current going through it, and they tell us that we have this equation that can be represented by it using Kirchhoff's second law. In AICE, you don't have to worry about how to get that equation, but you hopefully can understand and see how that equation can represent something, because this looks like a line, and they just graphed a line, okay? Look at what they plotted on the y value. They plotted r on the y value, so this is y. Look what they plotted on the x value. They plotted 1 over I. That means that r is equal to 1 over I. That's the x value. That's the y value. That means that the m is going to be e. See how it's like e times 1 over I? E over I is the same thing as e times 1 over I. So this is going to be our slope is going to be e, probably our complete electromotive force, the EMF, minus r. That is the b. So the y-intercept in this equation is representing the internal resistance of the battery. So the very first question, it says, state the internal resistance of the battery. That just means, what is the y-intercept? And if you look carefully, it is right there, which ends up equaling... Anybody can see it? It looks like it is... Oh, boy. That's hard. That's 1.5 or 0.6. I'm going to go with 0.6. There is another way that we could do it. That would be, you could take the equation and plug in a point and then have two variables if you didn't see that it was going to be the y-intercept. So if you look at r, we have r at 0.5 is equal to... No, r at 0.5 is equal to... Oh, gosh, that's hard to see. We'll just say 5.8 or 5. That looks like 5.6. E, we don't know. 1 over I, if you do 1 over 0.5, you get 2 is equal to I. You could plug in 2, and then you have two variables here, and you just plug in another point, and then you can use system of equations. But that takes a little bit longer, but it is possible. All right? I think we're going to have to do that to determine the E anyways. So, actually, wait a minute. E is the slope. So what's the slope in this equation? We went up by, from here to here, we went up by 5.6 and over by, like, not 0.5. Well, I guess we could say we went up by 6 and over by 0.5. Up by 6, over by 0.5 ends up equaling 12 volts is equal to the EMF. All right? 12 volts is equal to the EMF. We haven't done part 1, though. Use the figure to determine the power dissipated by the variable resistor when there is a current of 2 amps. Power is equal to a lot of things. I times V, or I squared times R, or V squared over R. Based on the fact that we have current and resistance, I'm going to use the I squared times R1. The current going through it is 2 amps, so that'd be 2 squared. What is the resistance when the current is 2? You got to be careful. When the current is 2, 1 over I, 1 over 2 would be 0.5. And then you find that the resistance, I think it's 5.6. It's actually 5.4. You'd multiply by 5.4 there. 2 squared times 5.4 ends up equaling a power of 22 wattos. I almost spelled wattos. That would be embarrassing. And that's going to do it. 30 minutes, 34 seconds. Stay positive.